Our group will presenting about the dynamic of particle, which is chapter 4 during our previous lessons. So in this presentation, we will explore the fascinating world of dynamic particle. From Newton's law, we will take a detailed look at the theory and application of particle in motions. Before starting our presentations, I would like to give the definition of a particle first. So, a particle is a small object used to represent an object motions whose size and shape can be neglected. And the other one is, I would like to introduce about the concept of motions. Motion is a change in position of an object over time and can be described in terms of displacement, velocity, and accelerations. And there's a ton of Newton's law of motion, which is Newton's first law, Newton's second law, and Newton's third law. The foundation of dynamics. This law describes how force affect the motion of a particle.
Now, I want to tell you about the Newton's first law. The law of inertia, also known as Newton's first law of motion, tells us that objects like to continue doing what they are doing. If something is at rest, it wants to stay at rest. And if something is already moving, it wants to keep moving in a straight line of a constant speed. It's like an object has a natural resistance of change in its motion. It takes an internal force to make them stop moving, or change their direction. So, inertia is about resistance to change in motion. And the derived formula of Newton's first law is. Now, I want to show you an example for a Newton's first law. Let's go. Now, this video shows two people pass a ball back and forth. When the first person throws the ball to the second person, the ball continues moving in the air due to its inertia. It wants to keep moving in a straight line until the second person catches it, or another force like a resistance slows it down. The ball inertia helps it maintain its motion until acted upon by an external force.
For the next experiment is the coin drop experiment. This experiment is very safe that even kids could do this experiment. All the apparatuses that we need are just a piece of paper, a mark, and don't forget our main star, that is a coin. To explain the coin's behavior, we need to refer from the Newton's first law of motion. The law states that an object at rest will remain at rest, and an object in motion will stay in motion with a constant velocity, unless acted upon by a net external force. At first, the coin was in rest state, and when you pull the paper, the gravitational force will act on the coin as the external force pulling it downward, because there are no more normal force that oppose the gravitational force when you remove the paper surface from the system. Prior to release, the coin has inertia, resisting any changes in its state of rest. Once dropped, the coin's inertia opposes the force of gravity, causing it to accelerate. Understanding this interplay between inertia and external force help explain the coin's motion during the experiment.
Okay, now I will share about second law. Newton's second law of motion about the behavior of object for which all exciting force are not balanced. The second law states that the acceleration of an object is dependent throughout two variables: the net force acting upon the object and the mass of the object. The acceleration of an object depends directly upon the net force acting upon the object, and inversely upon the mass of the object. As the force acting on the object is increased, the acceleration of the object is increased. As the mass of an object is increased, the acceleration of the object is decreased. Okay, example, when riding your bicycle is a good example of this law of motion at work. Your bicycle is the mass. Your leg muscle pushing on the pedal of your bicycle is the force. When you push off the pedal, your bicycle acceleration. You increase the speed of the bicycle by applying force to the pedal. Newton's second law also say that the greater the mass of the object bearing acceleration, the greater the amount of force need to the acceleration the object.
Now I will continue about Newton's third law. Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that whenever two objects interact, there exert equal and opposite force on each other. These forces are called reaction pair. Now, let's apply this law to the scenario of someone trying to push a wall. When someone tries to push a wall, they apply a force on the wall. The wall also applies an equal and opposite force on them. This is why they feel a pushback from the wall. The net force on the person is zero because the force cancels out. However, this does not mean that the person stops moving. They are still accelerating in the direction of initial push because they are moving in a different direction than the wall. So, if someone tries to push a wall with a force say 10 Newton to the right and the wall exerts a force of 10 Newton to the left on the person, despite the person applying force, the wall doesn't move because the reaction force from the wall cancels out the action force from the person. In this case, the person and the wall experience equal and opposite force. But since the wall is much more massive than the person, it doesn't accelerate noticeably. In summary, Newton's third law explains the interaction between two objects by emphasizing that the force they exert on each other are equal in magnitude and opposite in direction.
As conclusion, the dynamics of a particle experiment can yield insight into its motion, interactions with forces, and potential energy changes. Observation may provide information about the underlying physical principles governing the particle's behavior, such as Newton's law of motion or principle from quantum mechanics. Analysis of experimental data allows scientists to draw conclusions about the forces acting on the particle and its trajectory in different conditions.